All right, hello everyone. My name is Reese. I'm your TA. Hopefully you've already watched my discussion one video and introduction and know that already. But anyways, this is my recording for discussion number 2. Most of you have been in my Zoom call this week and have seen at least the first half of it live. So I will be re-recording that first half and then also adding that second half. So if you feel comfortable with that first half, feel free to skip through until I begin going over the case study. So before I hop on in, just in case you were not able to attend discussion on Zoom this week, I did want to point out some housekeeping things. First of all, I wanted to let you know that discussion is beginning in person next week. So this will be our last Zoom week. And I have 4 different sections. So I'm going to pull up Canvas so I can show you these 4 different sections I have and where to find all of this information. And then after that, we'll get into the worksheet itself. So on your Canvas, if you go to the modules tab, there will be a discussion tab. I'm on just one of the 3 Canvas sites, so you might not be in discussion 49025, you might be in 49000 or 05 or my other section, but just it'll look the same on each site. If you open this up, what you'll see is that I have this discussion information sheet. I think there's been an issue with downloading this to your computer, but that's totally fine because all of it is copied and pasted right into here. So if you can't get this document open, that's totally fine. What I would do is just copy and paste it into your own Word document and save it. I teach 4 different sections. I teach a Monday 1 to 2 p.m., a Tuesday 1 to 2 p.m., a Wednesday 1 to 2 p.m., and a Wednesday 2 to 3 p.m. So again, starting next week, all of those will be in person. If you ever have a day where you cannot make it to discussion, whether you have an appointment, an interview, or not feeling well, etc., definitely feel free to attend any of my other sessions for that week. Maybe just shoot me an email ahead of time. Normally won't need to respond to it, but when I see it, I'll know it. Another thing I wanted to point out is that attendance is expected but not mandatory. I will make a list of who attends each discussion because that is who will get the recording link. So if you do not come to discussion without letting me know why beforehand, I will not be sending you the recording, and therefore you will miss the discussion for that day. This class is a pretty difficult class, and you really need to make the effort to come in person and participate. When we're in the classroom, I ask that you are not like playing on your cell phone. I, of course, understand if you need to look down at a text every now and then, but please don't be texting and please be respectful of others when we're in the classroom. I've gotten a few emails asking if it's okay if you use tablets or electronic devices to take notes. I'm totally fine with that. I use my iPad to take notes. I'll be using it in the classroom as well. So there's no issues with using tablets, laptops, or whatever to take your notes. So each section might have a different UGTA, the TA, and I will explain that more once we get back in person. But for now, just know if you're receiving this recording, I am your discussion TA. You might have a different lecture TA. If you're in the 8 a.m. section, Daniela is your TA. If you're in the 9:30 a.m. section, Tianyu is your TA for lectures. So that means they're going to proctor the exams, they'll grade the exams, they're in there with Dr. Chang every now and then. I am your TA for the discussion portion. So that might get a little confusing. I'll explain it some more next week. But again, I am your TA for the discussion portion. Awesome. So this class, we have 12 different worksheets. Today, we're starting on the second one. Discussion worksheet number 1. I sent out the recording last week. However, I will be re-recording that. So I will be re-recording discussion number 1. I'm going to create a PowerPoint to explain it a little further and more in depth because it is a pretty complex worksheet and I really want y'all to understand this material. All right, so that's enough from me. Let's go ahead and hop into discussion number 2. Oops, wait, just kidding. I forgot one other thing I wanted to point out. So under the modules, under my module, make sure you're looking at the correct discussion. Again, you might be in one of my other 3 sections, so it could just have a different number here. But as you see, I organized it into our 4 different units, and here is where I will post the recordings and other things, and here are the worksheets. Now, again, there are 12 worksheets in total. I would not recommend printing them all out right now. I would recommend printing them out maybe the weekend before class, because as you see with discussion worksheet 2, I changed it up a little bit from the original worksheet. All I did was add space for notes, add space for calculations, things like that. If you have already printed them all out, that's totally fine. Just bring some extra paper with you to class to jot down some notes. I would always have extra paper just in case you write too big and underestimate how much or don't have enough space in the space I gave you. So always come to class with some extra paper to take notes. All right, so now we will finally hop on into the worksheet. So let's go ahead and begin. So this is worksheet number 2, discussion number 2, and today we are going to be looking at osmolarity and tonicity. So there are 5 solutions that are really important to know before we hop on into this. First, we have NS, which stands for normal saline. Then we have half NS, half normal saline. D5W, which is D5 water, or 5% dextrose in water. We have D5 half NS, which is half normal saline and that D5 water, and then D5 normal saline, D5 and normal saline. So those are just the abbreviations and what they stand for. We're going to go further in depth with each of these, so you will definitely be seeing them again. Before we look at those though, let's do a quick review of molarity and an intro into osmolarity. And then on the next slide, we're gonna look at osmolarity and tonicity. So molarity, what is it? It's a measure of the concentration of a chemical species or the amount of substance per unit volume of solution. Now, I personally am not a big fan of scientific definitions like that, so don't worry about memorizing that. I just wanted to add that in there in case that makes sense to you. What's important to know is that we see that molarity is expressed in moles per liter or moles. And one thing that goes along with molarity is the molar masses of 2 very important substances that we're going to use in our calculations today. So these you definitely need to memorize. So the molar mass for sodium chloride, aka salt, is 58.5 grams per mole. And for glucose, it's 180 grams per mole. So you definitely need to have that memorized for exam 1. Next, we have osmolarity, which is a measure of the solute concentration or the total number of solute particles per liter. What's more important here is to know that it's expressed in osmoles, and we'll also see milliosmoles. Now, molarity tells us the condition or the concentration of a chemical species. Osmolarity is kind of telling us the concentration of a solute in the body, so the conditions of the body. So in this class, we're not so much focused on molarity, we're way more focused on osmolarity. And the way that we convert from moles to osmoles or go from molarity to osmolarity is by multiplying by the dissociation factor. So when we hop into our calculations in just a little bit, we'll see how that works. So there are 2 dissociation factors that you definitely need to memorize, first being sodium chloride and the second being glucose. And if you're wondering what that means, what dissociation factor means, it just means whenever we put it in a certain solution, it's going to dissociate into 2 different molecules. So sodium and chloride will dissociate. Glucose is a monosaccharide, so it just dissociates into 1 molecule. All right, so definitely have those memorized, but once we work through these calculations, I think you'll get it down. So now we're going to look at tonicity and a little more on osmolarity. So I bet a bunch of you are familiar with tonicity, and what it is it's an indicator of the cell's behavior or the effect of a solute on the ICF, the intracellular fluid. So intracellular fluid inside the cell, that's going to be cell behavior. So if it's less than 300, we see that the body cells are at 300 milliosmoles. If we administer some type of solution, that will cause the body cells to swell. This is a hypotonic solution. If it's equal to 300, they'll remain the same, an isotonic solution, and greater than 300, they will shrink because it's a hypertonic solution. Now, a silly mnemonic that I use to kind of remember hypo and hypertonic is hypo-hippo. Hippos are below the water, and they are pretty swollen. They're pretty big animals. They're huge. So hypo-hippo, hippos are below, so below 300, below the water, and they're pretty big and swollen. Also, the letter O is like a swollen looking, like you can think of a swollen cell. Someone else earlier gave you the mnemonic of, you can think low or below and hypo, they rhyme. Hypo, below, hypo, low. Iso, equal, that one's easy to remember. And then hyper, I always remember that an E kind of looks like a shrunken O, so a shrunken, cell. And then you can think like people that are really hyper, they're always on top of things. They're always above, above everyone on the next level. So hyper, shrunken E, and above. All right, so moving on to osmolarity, what we see is the osmolarity of the body is also at 300 milliosmoles. So the tonicity of the body cells and the osmolarity of the body are both 300 milliosmoles. The same thing applies here, and this should say hypoosmotic, isoosmotic, and hyperosmotic, not tonic. I guess I copied and pasted those and forgot to change it. And again, one important thing to remember is cell behavior is determined using tonicity, not osmolarity. So when we work on filling in our chart, that's definitely something you're going to want to think about. All right, so let's go ahead and hop on into it. So again, moving back to those 5 important solutions. These are the solutions we're going to fill into that first chart. So starting with normal saline, what is it? Normal saline is also called 0.9% saline, sodium and water, or sodium chloride and water, salt and water. The technical, broken down version of what we're talking about is 9 grams of sodium chloride and 1 liter of water gives us normal saline, or 90% saline. So this is definitely something you're going to want to know. You're going to want to know that there is 9 grams of sodium chloride or salt in 1 liter of water, because we're going to use that in our coming calculations. Moving on to those calculations, what we're trying to get to is the osmolarity. We're trying to solve for the osmolarity of normal saline. And to do so, we use a 3-step process. First, we solve for molarity, then we solve for osmolarity, and then we convert our osmoles into milliosmoles. So let's begin. So when solving for molarity, we're going to take that 9 grams of sodium chloride, and because that's in 1 liter of water, and we're going to divide it by that molar mass that we looked at the beginning, that 58.5 grams per mole. Again, that's the molar mass for sodium chloride. If you're wondering how we get that, it's just by adding the 2 molar masses of sodium chloride together from the periodic table. Whenever you divide these, what you're going to end up with is 0.15 moles. So the molarity is 0.15. Now, think to yourself for a second, how do you remember what I said at the beginning, how we go from molarity to osmolarity, how we move from moles to osmoles? What do? We multiply by the dissociation factor. So what we do is we take that molarity we solved for and we multiply by the dissociation factor, which for sodium chloride was 2, because sodium is going to split into 2 different molecules or dissociate into 2 different molecules when dissolved in a specific solution. So when we calculate this out, what we get is 0.3 osmoles. Let's put that into more realistic terms by multiplying it by 1,000. And what we get is 300 milliosmoles. So milliosmoles is normally the unit that we use when talking about osmolarity and tonicity. So I definitely use this three-step process when first working through these calculations, but once you get comfortable with them, you can kind of simplify the process into one equation, solve for molarity, multiply by the dissociation factor, multiply by 1,000, and you'll get the same answer. So let's go ahead and start on the worksheet. So this is going to be the first column of that chart. So what we see is that the solution we're working with is normal saline, that's a given. And we just solved for the osmolarity, which was about 300 milliosmoles. If you use this simplified equation, you would get about 307, as long as it's not greater or less than about 20 to 30, milliosmoles. It's not going to have a huge effect on that number. So we can just round it out to around 300 milliosmoles. So what type of osmotic solution would this be? Hypo, iso, or hyper? If you remember back to what I said at the beginning, the body's osmolarity is 300 milliosmoles. What we just solved for was 300 milliosmoles. So that would make it an isoosmotic solution. Same with tonicity, we have an isotonic solution because the body's cells are also at 300 milliosmoles. So again, the tonicity is what determines the cell behavior, and an isotonic solution is going to cause the cell to remain the same or have no change. That's the effect on the intracellular fluid. There is no change because it's an isotonic solution. All right, awesome. So that's that first column of the chart. Let's go ahead and move on. So now we're going to look at half normal saline. Half normal saline, what is it? It's 0.45% saline. So normal saline is 0.9% saline. Divide that by 2, you have half normal saline. So what we see as half normal saline is 4.5 grams of sodium chloride in 1 liter of water. That's not as important to memorize as the 9 grams, because if you know the 9 grams, you can just divide it by 2 and figure out that it's 4.5 grams of sodium chloride in 1 liter of water. So let's go ahead and plug this into our chart. We don't need to do any calculations here because we can easily figure out the osmolarity by just dividing our normal saline by 2, giving us 150 milliosmoles. So what type of osmotic solution would this be compared to the body? 150 milliosmoles, hypo, iso, or hyper osmotic solution? It's going to be a hypoosmotic solution. Hypo, hippo, hippos are below the water. Hypo, low, it's below 300. So that makes it an hypoosmotic solution. Same thing with tonicity. It's a hypotonic solution. And we know that tonicity is what we use to determine cell behavior. So a hypotonic solution will do what to our cells? It will cause the cell to swell or hemolyze. Dr. Chang likes to use the word hemolyze. So hemolyze is specific to the red blood cells. Heme means blood. So hemolyze, the cell is going to swell. All right, awesome. So that is the second column. Let's move on to our next solution. So now we're looking at a different type of solution. We're looking at D5 water. What is it? It's 0.05 or 5% dextrose in water. Dextrose is a type of sugar, and all sugars are broken down into glucose. So we're going to use glucose to solve for these. We're going to use the molar mass of glucose, and you really use the term glucose when working through these. Again, dextrose is a type of carbohydrate or sugar. All sugars are broken down into glucose, so it will eventually get there. So what is it? It's 50 grams of glucose in 1 liter of water. That's going to give us D5W, D5 water. So that 50 grams of glucose, I would definitely memorize that. So let's do some calculations. Again, we have that 3-step process: molarity, osmolarity, and conversion into milliosmoles. So how do we solve for molarity? We take the grams of glucose in our solution, we divide it by its molar mass, which is 180 grams per moles, and what we get is 0.278 moles. That is our molarity. How do we go from molarity to osmolarity? Moles to osmoles, we multiply by the dissociation factor. Hopefully you're saying all this along with me. What's the dissociation factor for glucose? It is, 1. So it's 1. So our molarity and osmolarity, same number, but now we're in terms of osmoles. I added these, chemical molar masses up here, just in case you're wondering how we get that molar mass. But definitely you don't need to worry about memorizing that or really understanding that. We're just adding the molar mass of these substances. But okay, so we now have our osmolarity in terms of osmoles. Let's convert that into milliosmoles by multiplying by 1,000. And that we get our osmolarity of 278 milliosmoles. Here's our simplified equation once we kind of get more comfortable with working through these. And now we can plug it into our chart. So this is going to be that third column of the chart. So we're working with D5 water, and we just solved for the osmolarity of 278 milliosmoles. So 278 milliosmoles, when comparing that to the osmolarity of the body, we could say that's hypoosmotic to normal. It doesn't have a huge difference. On the exam, it's going to be a very clear difference, like 150 or 400 and whatever. So don't worry about these examples that are a little bit closer. On the exams, it will be very clear whether it's hypo, iso, or hyper. But technically, we could call this hypoosmotic to normal. The tonicity, it's going to also be hypotonic, but I want you to make a note here because we're going to return and add an extra little piece to the reasoning behind the hypotonic answer here. Hypotonic solutions, we just discussed this. What do they do to the ICF or the intracellular fluid or the effect on the cell behavior? It will cause the cell to swell or hemolyze. All right, awesome. So now we're going to look at D5 half normal saline, which sounds like a really big word, but all it is that D5 and that half normal saline that we've already looked at. So that 5% dextrose and half normal saline. It's 50 grams of glucose and 4.5 grams of sodium chloride and 1 liter of water. Again, you don't really need to memorize that because we already know that we have 50 grams of glucose in D5 water, and we have 4 grams of sodium chloride in half normal saline. So let's plug this in. So since we've already solved for D5 and half normal saline, we can easily calculate the osmolarity of D5 half normal saline by taking that D5, adding that normal saline, and getting 428 milliosmoles. So all we did here was add those together to get 428 milliosmoles. Now, when comparing 428 milliosmoles to the osmolarity of the body, would this be a hypo, iso, or hyperosmotic solution? This would be a hyperosmotic solution because it's above. It is above. However, I'm assuming that when I ask you what type of tonic solution this would be, you would also say hyper. However, there's a very important factor that we need to consider. It's going to be a hypotonic solution because glucose is a non-penetrating molecule, meaning that it's not going to enter the ICF. It is not going to enter the cell. It can leave the cell and be carried into the blood, but it cannot enter into the cell. It's non-penetrating. Therefore, when we're solving for the tonicity, the cell behavior, we need to subtract that non-penetrating molecule, D5, dextrose, from our original osmolarity to solve for tonicity. So let me change my pen here so I'm not writing with a highlighter. What we would do is take that 428, our original, we would subtract the D5 water, the glucose, the non-penetrating molecule, and what we're left with is 150 osmoles. 150 osmoles is less than 300, and when comparing that to the tonicity of the body cells, what we see is that makes it a hypotonic solution. So you don't want to forget to do that on your exam. If you forget to subtract those non-penetrating molecules when determining tonicity, you will not get the answer correct. So make sure you remember that glucose, D5, is a non-penetrating molecule. Therefore, when we're looking at the tonicity, the intracellular behavior, we need to subtract that. That's why I wanted you to make this extra little note up here, because yes, D5 water is a hypotonic solution, but we wouldn't be thinking of it as 278. We would be thinking of that original osmolarity of 278. We'd subtract our non-penetrating molecule, glucose, and be left with 0. 0 is still less than 300, so it would still be a hypotonic solution. But make sure you know that we're comparing it to 0 and not 278 when looking at the tonicity of D5 water. So we've seen this twice now. You should have it down at this point, and I see that this should say hypotonic up here. Messed that up. But a hypotonic solution, what is that going to cause the cell to do? Swell or hemolyze. Awesome. All right, so now we're going to move on to our last solution. So now we have D5 normal saline, 5% dextrose and 0.9% saline, 50 grams of glucose and 9 grams of sodium chloride and 1 liter of water. So we don't need to do any calculations here because we've already solved for D5 and we've already solved for normal saline. So we'll take that normal saline, we'll add that D5 water, and what we get is 578 milliosmoles. So when comparing this to the osmolarity of the body, it will be a hyperosmotic solution. When comparing it to the tonicity of the body cells, take a second here and think about what it would be. Hypo, iso, or hyper. What do we need to do to figure that out? We subtract our non-penetrating molecule. So we take that original osmolarity, we subtract our non-penetrating molecule, which is that D5 water, that glucose, and we're left with 300. 300 is equal to this tonicity of the body cells, making an isotonic solution. An isotonic solution does what to the cell? It causes no change. The cell will remain the same. So a little example here, if you're wondering a little bit more about osmolarity and tonicity, just to put it into kind of a more visual term, you can think about going somewhere like Chick-fil-A and getting a really salty food and a really sweet drink. So D5, a really sweet something, sugary something, and something really salty, normal saline, salt water. Whenever I eat something really salty and drink things really sweet, I bloat. My fingers feel swollen, my body feels swollen. I feel like I'm carrying a lot of water weight, but the behavior of my cells is not changing. It's not like when I go and eat a salty and sweet meal, my cells will swell and burst or shrink and crenate. No, my cells are going to remain the same. I'm not changing the conditions of my intracellular fluid. Instead, I'm just adding some fluid to my body. I'm changing the osmolarity of my body. I'm just holding on to some extra water, some extra penetrating, molecule. However, I'm not, causing my cells to swell and burst or, shrink and die. That's not what happens when I have, a salty and sweet meal like D5 normal saline. Now, in some cases, people do need the solutions that will cause their cell to swell or shrink. If someone drank way too much water, like in that, I don't know if y'all have ever heard that story where this radio show hosted a challenge to see who could drink the most water. And this person was drinking so much water that their body became in a really extreme condition and their cells were extremely swollen. They would need to be administered something that would cause cause their cells to shrink, they would need to be administered a hypertonic solution. If someone was really dehydrated and their cells were already shrunken, they would need to be administered a hypotonic solution to get those cells back to their regular size. So one thing we didn't see on here is an example of a hypertonic solution. But again, hypertonic solutions will cause the cell to swell, and Dr. Chang likes to use the term crenate. I'm sorry, hypertonic solutions make the cell shrink, and Dr. Chang likes to use the word crenate. So crenate, you can think like cremate, like cremation, you know, the body shrinks into ashes. Kind of the same thing with cell. Crenate, the cell shrinks and dies. All right, awesome. So that is the chart for the first half of this worksheet. So this is where we've gotten in discussion this week. So this is going to be your starting point for the recorded half. So what we're going to do now is look at a case study. We're going to look at this in more applicable terms, kind of in an extreme case. So what we have, sorry, I need to get my pen off so I can click on the screen. What we have is this guy who gets attacked by a wild animal on his trip to Africa. And when this happens, he did not die, but he lost an extreme amount of blood. He's hemorrhaging, he's bleeding out. Luckily, he's treated at a local clinic. However, the medical personnel's credentials are a little obscure. And what we're going to see is they don't exactly treat him correctly. So luckily, you know, we're at the stage in our scientific career where we can start to solve things like this, where we can look at data and statistics to figure out what he was treated with, whether it was correct or incorrect, and what he should have been treated with. So let's hop on into it. So here are the statistics that we are given. We are given Dave's normal statistics and then his statistics after blood loss. So what we see is he lost some weight, you know, indicator that he, you know, lost blood. We can see that his plasma osmolarity remained the same. We see that his blood pressure decreased significantly, and that his concentration of sodium in his plasma increased just a little bit. So to work through this problem, I'm going to go ahead and switch over to the discussion worksheet itself. So let me share my iPad screen. Okay, awesome. So I am now pulling this up on my iPad. We are down here to our case study. So the first thing we're going to do when working through problems like this is we're going to convert his weight from pounds to kilograms. So we're going to go from pounds to kilograms. Use a different color here. Use green. So what we need to do is convert that 175 pounds into kilograms, and to do so, we divide by 2.2. So whenever we divide by 2.2 to convert into kilograms, what we're going to get is 79.55 kilograms. So that's Dave's initial weight. So what we're going to do is we're going to take that and we're going to go ahead and plug it into our chart. So what we see is that we are given his inulin volume. Inulin volume stands for, I should have given myself a little bit extra space here. Let me move this down quickly so you can make a note here. Inulin volume is telling us the volume of his extracellular fluid, or his blood, so ECF or blood. So what we're going to do is we're going to take that 79.55 kilograms, and to solve for the volume of his total body, we will subtract, or sorry, multiply. Okay, I am messing up here. Go ahead. I'm going to try and edit this out. If I can't, we're gonna restart the steps right here. Give me just a second. Okay, so now we're going to begin the case study. I apologize for that. I decided to take a different approach to teaching this. So let's go ahead and begin. So again, we've already looked at his statistics, and now we need to work on filling in this chart so we can begin solving for his starting and post condition. So let's go ahead and plug in what we already know. So we're looking for the volume, the solute or the amount of solute, and the concentration in terms of milliosmoles. So we know that we're for sure already given his osmolarity in terms of milliosmoles. So we can go ahead and plug that in. So 305, 305, and 305. We also are given the volume of his extracellular fluid. So I want you to make a little note here. I guess I'll kind of try and color code this. I want you to make a note here that this inulin volume stands for extracellular fluid volume or blood volume. So inulin means the extracellular fluid or the blood. So here we are also given his extracellular fluid volume, so we can plug that into our chart and have a nice little starting place. So we've plugged in all of our givens, and now we need to solve for the rest of them. So let's start by solving for his total body volume. So how we solve for this is we take his weight, which is 175 pounds, and we divide it by 2.2 because we need to convert it into kilograms. When we do this, what we get is 79.55 kilograms. So we get 79.55 kilograms. Now that's not his total body volume because we need to get rid of that total body water. So we need to multiply it by this total body water right here. So 60%, what we're gonna do is we're gonna take that 79.55 kilograms and multiply it by 0.6. When we do this, what we end up getting is 47.73 liters. So 47.73 liters. And that tells us the overall volume, his body volume. So we're gonna plug this in to our chart that we just solved for, 47.73. And one cool thing is that whenever we have two of these columns filled in, we can solve for the other. So let's subtract the total volume, or let's subtract the extracellular fluid from the total. And what we get when we solve through this is 31.73 liters. So we've solved for the intracellular fluid by solving for his total body volume, subtracting the extracellular fluid volume, our inulin volume, and that gave us our intracellular volume. So now that we have two in each column, we can solve for this middle column. So if you remember back to last week, which if you don't, that's okay, I'll be making another recording. We have this really cool equation to help us solve for solute volume or concentration. And the equation looks like this. I'm gonna write it up here. C equals S over V. What that's telling us is concentration equals solute amount, normally in osmoles, over volume. So volume. Solute over volume. And if you look at our chart here, our three variables are volume, solute, and concentration. So all we need to do is plug these variables into this equation and we will be able to solve. So C equals SV. I'm going to write that here. And let's see, I'm going to space this out. C equals S over V. We're given the concentration, which is 305. We are given the amount, or no, we're not given the amount of solute, so that's our X, but we are given our volume, which is 47.73. So when we manipulate this equation, what we get is X equals 3. Oh, and one other thing to add, sorry guys, is this should be 0.305 because we're in osmoles, not milliosmoles here. So we convert that 305 milliosmoles into osmoles by just dividing by 1,000. So what we get is 0.305 times 47.73, and that will give us our answer of 14.56 osmoles. So this right here is our final answer. Sorry, my handwriting is so bad on the iPad. It's like the pen like makes my hand shake or something. Okay, so cool. I'll work out one more and then I'll leave you the last one to work out. I'll give you the answer, but I want you to try working it out on your own. We'll now solve for the extracellular fluid solute amount. So again, we have that C equals S over V. We're given concentration, which is 0.305 because we're working with osmoles now. We're going to solve for our solute amount, and we will divide by our volume, which is 16. So what we get when we manipulate this equation is X equals 16 times 0.305, which will give us 4.88 osmoles. So that's the amount of solute in his extracellular fluid. So I want you to use that equation once more to solve for the intracellular fluid. I'm not going to work it out, but hopefully you can figure it out by now. And what you're going to get is 9.68 osmoles. So that's how much solute is in his intracellular fluid. Okay, cool. So now we need to solve for the conditions after his blood loss, his hemorrhaging. So again, we're going to go plug in our givens. So what we see is that the plasma osmolarity is the same. That is something that we need to take note on. So whenever we see that the plasma osmolarity is the same and it's very close to the osmolarity of our body, this tells us that his body is in an isotonic state. His cells are in an isotonic state. This is an isoosmotic condition, or isotonic condition because he's losing blood. He's losing blood from his body. He's not changing the conditions of his cells, however. So this is an isotonic issue. Hemorrhaging, blood loss, is an isotonic issue. So again, we see that his plasma osmolarity is the same. So switching back to green, we can plug that in to our chart, 305, 305, and 305. Now we are not given his inulin volume post blood loss, so we're going to solve for it, and we're also going to solve for his new body, total body volume. So let's take some steps to do so. So the first step is figuring out how much his weight changed. So we're going to take that original 175 pounds, subtract the new weight, 171.7 pounds, which is going to give us 3.3 pounds. When we divide that by 2.2 to get into kilograms, what we get is 1.5 kilograms. So that means he lost 1.5 kilograms of body weight. You can also think of this as 1.5 liters lost of ECF, of blood, because we know he's not losing intracellular fluid because his osmolarity has remained the same, making it isotonic. So he's not losing ICF, he's losing ECF blood. So let's go ahead and use this to work on our chart. So when we subtract that 1.5 kilograms from our original body weight, sorry, again, handwriting is so bad on the iPad. What we get for his new total body volume is 46.23 liters. So that's his new body weight. When solving for the extracellular fluid loss, we know we lost 1.5 liters of extracellular fluid from that wild animal attack. So we take that 16, we subtract that 1.5 liters, and what we get is 14.5 liters. And now that we have 2, we can solve for this last one. So all we do is subtract the extracellular fluid from the total body volume. And what we end up with is 31.73. So notice that the intracellular fluid volume is the same as it was before, meaning this is an isotonic condition. The cells were not affected, however, the osmolarity or the conditions of the body were. So now that we have 2 in each of these, we can solve for the middle variable by using that same equation from above. That's C equals SV. I'll work out 1 and then leave the rest of you to do on your own. So C equals SV. We take the concentration, which is 0.305, because again, we are now in osmoles. You'll set that equal to the solute amount, which we are solving for, divided by the concentration, or sorry, the volume, which is 46.23. And what we end up getting is 14.1 osmoles. So total body total amount of solute in the body is 14.1 osmoles. Use that equation for the next 2 and you can easily solve them. We have 4.88 osmoles here, or sorry, 4.42, oops, 4.42, and then 9.68 here. So that is the chart. So that's some pretty complicated math. So definitely make sure you practice this a few times. You're really going to want to know this equation here, concentration equals solute over volume. You're going to want to know how to convert from pounds to kilograms. You're going to want to know that you need to multiply by that normal total body water to get that total body volume. And then you need to know how to manipulate the chart to solve for the other unknown variables. Awesome. So now we can answer our first word problem on this case study. By how much, change my pen color. By how much, if any, did Dave's extracellular solute change? So if we look at his original extracellular fluid solute, which was 4.88, and we subtract that 4.42, what we're going to see is that it changed by 1.5 liters. So, excuse me, you're going to want to look at the volume instead. So the volume, not the solute. So I guess Dr. Chang wants this in the volume. So I think it should say extracellular fluid volume. How much did the intracellular fluid volume change? 0. It changed by 0 liters. So we see no change here. Again, telling us that this is isotonic. This is an isotonic condition. Hemorrhaging is an isotonic solution. So now we're asked to briefly explain the rationale behind your answer to part A. It's not all just a calculation. Let's understand the reasoning behind the calculation. So Dave lost blood. And I remember that I actually made a PowerPoint for this. So I'm going to return to PowerPoint. So Dave lost blood. And blood is an isoosmotic solute in the extracellular fluid. Therefore, it does not change any component in the intracellular fluid. It's isoosmotic, isotonic. It's not going to affect that intracellular fluid. He lost blood. It's not going to change anything with his cells. It will change his extracellular fluid because he lost body volume. He lost weight. He just bled out blood. All right. So now looking at question 4, we see that he was treated with 2 liters of a selected IV solution. And we're left to determine what that solution was out of these 5 options. So what we see is that his plasma osmolarity decreased to 304 milliosmoles, and his intracellular fluid volume was 33.6 liters after he was treated with the selected IV solution. If you remember back, the original ICF volume was 31.75. So if you look back at that chart, it was 31.75 or 31.73 liters. So this tells us that whenever that total osmolarity decreases, we're dealing with a hypoosmotic solution. So they gave him a hypoosmotic solution because that original was 305. And this increase in ICF volume tells us that they treated him with some type of hypotonic solution. Therefore, water will enter the cell. The ECF will swell. Hypo, swell. So water will enter the cell after they gave him this 2 liters of selected IV fluids. So which of these solutions is hypoosmotic and hypotonic? Just so you know, this modified Ringer saline is 278 osmoles. We solved for the osmolarity of all of these earlier. So normal saline was 300, 5% dextrose was, what was it? It was something, I don't have it pulled up. We know all of these already from our calculations earlier. So which one of these would be hypoosmotic and hypotonic? That's going to be this modified Ringer's saline. It's 278 osmoles. It's lower than 300, the normal conditions of the body. And we don't see any glucose, or we do see glucose in here. However, that's going to just be subtracted from that 278, making it even lower, leaving us with an even more hypotonic solution. So we would subtract 25 from 278, giving us 250 something. I'm bad at doing math in my head, which is definitely a hypotonic solution. So this is what they gave him, modified Ringer saline. So do we think that this was the appropriate treatment for Dave? No. And let's talk about why. They should have administered an isosmotic and isotonic solution to replace that blood loss. Since they gave him a hypoosmotic and a hypotonic solution, he was not brought back to regular levels here. He still stayed above, and he was not treated correctly. They should have administered an isosmotic and an isotonic solution to replace that blood loss, that isotonic condition. Hemorrhage is an isotonic condition, so they should have treated him with an isosmotic and isotonic solution. Our last question is, if Dave were given an IV solution that was isosmotic but contained only water and a freely penetrating solute, what would happen to his ECF and ICF volumes and their osmolarities? So before we answer this, let's just review. A freely penetrating molecule will not stay in the ECF. It can move freely in between the ECF and the ICF, like water. So let's start with the ECF volume. If he was given an IV solution, of course, volume will increase. If you're given a solution of anything intravenously, your extracellular fluid, your blood volume will increase. If you put a needle in the vein and fill it up, the volume will increase. When looking at ECF osmolarity, what we see is that there will be no change. There will be no change. This is because it's not going to stay in the ECF or ICF. It's freely movable or freely penetrating. Yes, freely movable, freely penetrating. When looking at the ICF volume, it will also increase because we administered an isosmotic solution that's freely penetrating, so it can move into the ICF or the ECF, so the volume will increase. And ECF osmolarity there will be no change. Again, it can move back and forth. It's iso-osmotic, so it's not going to change the osmolarity. Alrighty, so we are all done. This was a tough discussion. My face is hurting from teaching this right now. I'm exhausted because that is a lot of work. So make sure you review this a few times before the exam. Watch this video a couple times. The parts of this worksheet that you're more confused on, definitely rewatch in the video, pause, take notes, work it out in your head. You can come to office hours on Monday from 2 to 3 p.m. and we can discuss it further if you'd like. I definitely recommend forming a group meet with each other, and if you have questions, you can ask each other. I think one of the best ways of learning is teaching. Why I'm a TA. So teach each other, answer each other's questions. It can really help you out. So again, next week we'll begin discussion in person. So make sure you know where the classroom is. It's a 50-minute class, so be there on time. We're going to start right at the dot. And bring that printed out discussion 3 worksheet with you. I wouldn't print it out until this weekend just because I might go and add extra space for notes, etc. If you want to print it out now, that's fine. Just bring a piece of paper with you. Lastly, feel free to email me with any questions, but if you have more advanced questions, please attend my office hours, or let's make an appointment to meet up, because answering really advanced questions over email is very time consuming. I have to put explanations into paragraph form, which takes a lot of time. So again, those more advanced questions, direct them to my office hours or to each other. But yeah, so that's all I have for y'all for discussion 2. And I look forward to meeting everyone next week in person. See you then. Bye.